Hey everybody, welcome back to another Robinson rant. And yeah, let's get going. So I've got some example problems to run for you. And before we get into that, let's go ahead and talk about an idea that comes up, and that is phasors. Okay. No, I'm not talking about Star Trek and Jean-Luc Picard and that kind of thing. No, this is the idea that electrical engineers use to talk about impedances. Now we've already basically discussed the idea. It's the idea that we go into the complex plane and model these oscillations in terms of a real component and imaginary component. And so based on that, these phasors are simply vectors in the complex plane. Okay, so that's the general idea about it. Now, the thing that I have not covered is that there are some very, for lack of a better term, useful properties that you can have dealing with vectors. Okay? And so let's go ahead and take care of some of those useful properties. So let's say for a moment that I have two vectors, and I'll call it vector A, and I'll label it as, I don't know, 1 plus I, and vector B, okay, which I will call, I don't know, I guess we'll call it 1 minus I, just for kicks. And if I go into my real and imaginary plane, my complex plane, and I start drawing these two vectors, you get some. So A is, let's call each hash mark 1/2. So vector A is up on this direction, right here, and vector B is down here. Okay, something like that. Okay. Now, first of all, let's go ahead. What happens if you consider vector A plus vector B? What should that equal? You got it? Yeah, good. And you know that according to our rules for vectors, we should add each component independently. In other words, we should take the real components and add them together, and the imaginary components and add them together. And so we get something like 1 plus 1 as the real component, and then the imaginary component, 1 minus 1. And excuse me, I accidentally used I there. So let's put J instead. Okay. So vector addition. And so you end up with something that says the two vectors added together gives you 2. Right? Completely real, no imaginary components at all. So we could do something like this. So it gives us, oops, there we go. We need one more hash mark, but at the end of the day, you get a vector of 2. Okay? Good. Okay. Well, let's go ahead and look at, that's not necessarily the most interesting property that we could examine. Let's go ahead and look at something slightly more interesting. Okay. And by slightly more interesting, let's go and first of all look at if I wanted to know the angle that vector A makes with the real axis. Go ahead, figure that one out. You got it? Yeah, good. Well, you know that the vector A, if I'm talking about the real axis, you take the imaginary part of A, you divide it by the real part of A, and you take the inverse tangent. Okay. So for this case, the angle that vector A makes with the real axis is simply given by the inverse tangent of 1, and that would be 45 degrees. Or if you prefer, pi over 2. excuse me, pi over 4. And you could do the same thing with vector b. Here we have to be careful. It's -1. And so you could write that as -45 degrees or negative pi over 4. Okay? Now here's the next piece. Here's the important part, the reason that phasors are somewhat helpful, okay, is unlike vectors, we can divide one phasor by another. So there is a slight difference about dealing with the complex plane as versus the spatial dimensions, x, y, and z. You know, for example, that if you are dealing with a spatial vector, say a vector r, which consists of an x component, a y component, and a z component, again, talking about physical space, you know that an operation like 1 over r is not valid, does not exist. That is a no-no. We are not allowed to divide by vectors. But these phasors, that is an okay operation, right? If I divide a number by, say, 1 plus I, algebraically, that's fine. In fact, we can do it in a way, we can algebraically manipulate this equation such that we end up with only a real number in the denominator, right? Namely, we multiply by the complex conjugate. And so what we can end up with here is this ends up giving us 1 minus I divided by 1 plus 1. So I'll go 1 minus I divided by 2. In other words, we can divide by a phasor if we want, and we can turn it into another phasor, right? I divided by my phasor A here in the denominator, and I can remanipulate it to turn it into a different phasor, which is somewhat nifty and not something that vectors can do, right? And we can go even further here. Okay, so I can divide by a phasor and turn it into another phasor, okay? Which means I could also do something like divide one phasor by another. So this was just 1 over phasor A. Let's go ahead. What happens if I take phasor B and divide by phasor A? Okay. Well, you can see already, we've already done phasor 1 over phasor A is simply 1 minus I over 2. And then if I multiply by phasor B, 1 minus I. And so what we end up with here, I'll call this phasor C. So you get FOIL, so we get 1/2, we get 1 minus 2I, and then minus I squared, which gives me, plus I squared, right? So what do we get at the end of the day here? We have 1/2 times 2I, negative 2I, because the 1 and the I squared end up canceling. So I get something that says negative I. Well, that's interesting. Let me ask you this. What's the angle that phasor C makes with respect to the real axis? If my phasor C is equal to negative I, what's the angle that C makes with respect to the y-axis? Excuse me, not the y-axis, the real axis. Yeah, you got it? Yeah, you notice that the angle that C makes is, we'll put pi over 2 here. That's the first question. Second question. How does the angle that phasor C makes with the real axis compare to the angles of phasor B and phasor A? And notice I said B and A. Okay? I don't mean just phasor B or phasor A. Yeah, hopefully you see it. Okay? And this is one of the nice useful properties of phasors, okay, is that the angle that phasor C makes is equal to the angle of phasor B minus the angle of phasor A. And now we've only done it for a specific, just a single instance. But it turns out that this works regardless of the two angles. Okay. And more specifically, when you're dividing two phasors, it's the angle of the numerator minus the angle of the denominator. Okay. That equals the angle of the resulting phasor. Pretty cool, huh? The other thing, notice, is that what happens, the magnitude of phasor C is simply equal to the magnitude of B divided the magnitude of A. And again, we've just done it for a specific case, but the magnitude of B was 2 square rooted. The magnitude of A is 2 square rooted. And so we end up with the magnitude of C simply being 1. So that being said, let me introduce you to some different notation. Okay. Generally, something like if we had our vector A, 1 plus I, or J, excuse me, keep falling into that vernacular. If you had A as 1 plus J, you could say that this is something like cosine of, let's say, 0 plus J sine of pi over 2. Could finagle it like that. And, yes, I see it. Right? Of course, this is not nice because you notice that the angle here is different for the cosine and the sine terms. So we could probably finagle our way to find something where we have the same angle. Okay? And the question then becomes, what angle is cosine of theta equal to sine of theta? You say, oh, okay, well, that's pi over 4. And the reason I say cosine of theta is equal to sine of theta is because the imaginary and the real parts have equal weights. Equal weights. In other words, yeah, there's a 1 in front of both of those. So instead of writing this as cosine of 0 j sine of pi over 2, because it has different angles, I could find a single angle that works for both of these. And again, it's based off of the equal weights. Now, of course, if you said, well, what happens if they're at unequal weights? That's fine. Say you have some vector D, some phasor D, where it's 2 plus j, unequal weights. So then I need to find at what angle 2 cosine of theta equals sine of theta. Okay. I'll get a different angle. I can still find the answer. Okay. So returning back to our initial one, I could rewrite this as cosine of pi over 4 plus j sine of pi over 4. And so you notice now, instead of having unequal angles, I have the same angle. And the only problem is that now the length of my vector is wrong, right? I went from cosine of 0, which equals 1, to cosine of pi over 4, which equals, yeah, you got it, 1 over root 2. So what must I do to my phasor to rescale it to the proper length? I multiply by the square root of 2. And boom, I've got it. You can see now that I have written the vector, rather than having two different angles and the same magnitude. Instead of having two different angles, I've rewritten it so that I have the same angle, and I have to simply scale the vector length to the right amount. It's cool. Now, the reason I go through all of this, is that this second representation is generally how you're going to see phasors. Okay? Rather than writing out this whole rigmarole, or conversely, you could simplify this to a degree. I could write this as root 2 using Euler's relation, j pi over 4. Okay? And using Euler's relation, you can do it like this, or more often, you'll actually see it written as something like the magnitude, okay, and this is the phasor notation. The magnitude, you'll see this angle bracket, and then pi over 4. Again, it's because the engineers, physicists, mathematicians were all completely lazy. These two expressions are equivalent. You can write it as components of a vector in the complex plane, the real component and the imaginary component. Or equivalently, you can write it as a magnitude times a direction. And that should sound somewhat familiar. Now you might say, does this always work? Of course, yes, it will. And the reason it will work comes back down to this question we asked ourselves at the beginning over here on the right-hand side. At what angle are these two components at the same weight? Or I gave a second example of, some different weight, some different proportionality. Okay? And the reason that you'll always be able to find an angle is that you'll notice you're always taking some sort of inverted cosine. Okay? If I move stuff over, you get something like 2 equals the tangent of theta. And the inverse tangent always exists. Okay? So what you'll end up doing is an inverted tangent of 2 equals theta. This inverse tangent will always exist for any value that you put in here. So let me go ahead now that we've discussed a little bit about the notation. Most phasors that you will run into will not be written in component form. Rather, it will be written in magnitude and direction form. The reason for it is that then it makes it very easy to do these processes, these multiplication or division processes. Okay. For example, go ahead, take a minute. We've already done vector phasor A as a magnitude and a direction. What's phasor B going to be written as? Yeah, you got it. Same magnitude, with a different direction. Okay. Now here's the power of having this phasor notation. And frankly, you don't have to memorize these. You could always go to the complex plane, work out your phasors, and then get these results back out. Okay. And here's the idea. We said, okay, we said C is equal to phasor B divided by phasor A. I will write that in magnitude and direction. I'll put my degree sign here. Magnitude and direction. And now we can apply the rules that we heuristically found. The magnitude of C is simply the division of the two magnitudes. The angle of C is simply the difference of the two directions. Of course, we did that for division. Okay. You could also do it for something like multiplication. Phasor A times phasor B. What do you think the result's going to be here? You got it? Yeah, good, 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 good. So multiplication, I'll write this out, 2 root 2 45. Yeah, you got it. You multiply the two magnitudes. So we get root 2 squared. And you, yeah, good, add the angles. Okay. So at the end of the day, we should get something like a magnitude of 2 with an angle of 0. So what I want to say is that this phasor notation isn't doing anything fancy. Okay? It's just a shortcut. So if you open up your book, you'll see this list of phasor rules. If this, then this, this, then this, this, then this. You can always simply go back to component form, plot it in the complex plane, and rederive these phasor relationships. Now, that being said, more often than not, as I've already hinted at, you will see phasor relationships given as magnitudes and angles. You say, well, why is this going to help me out? Okay. Let's take another example. Let's say for a moment we're dealing with the impedance of an inductor, which is written as J omega L. That's a component form. Go ahead, write this in phasor form, or excuse me, magnitude and direction form. You got it? Yeah, good. Let's start off with the direction. It's purely in the imaginary direction, which means our angle is 90 degrees. Yeah, very good, very good. And our magnitude, well, that's just the coefficient of my imaginary number. And so the magnitude will just be omega L. Yeah, good. How about ZC, the impedance of C? Yeah, you remember that's J omega C, which can be rewritten as negative J over omega C. And so what's that going to be equal to? Yeah, you got it. 1 over omega C times negative 90. Yeah, very good, very good. Yeah. Good. Good, 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 good. Sweet. Okay. So if you have something like a division process, these phasors could make it very easy. Let's go ahead and take another example. Let's say that you have a potential supply that is going at, I don't know, we'll make it easy. We'll say cosine of omega t. Okay? And it is hooked up to an inductor of inductance L. Okay. We can go ahead and use our phasor relationships. What's cosine of omega t written as a phasor? Yeah, you got it. Okay. And here comes the second piece. So V, we'll call it, it has a magnitude of 1. Notice I just left a 1 out here. Okay. And you could say that the angle in the complex plane is something like omega t. Right? If I use Euler's relation, it's e to the j omega t. And so you could say that that angle is constantly changing as time progresses. And in fact, I could go even further here. I could say it's omega t plus an initial angle, a starting angle of 0, right? 0 degrees. Okay. Of course, again, we've already got it written down. Our impedance, since we're now dealing with this complex plane, is omega L, and I'll put 90 degrees here. So let's say we're interested in finding the current running through the inductor. Well, because we have transferred this all into the complex plane, okay, I can write the impedance or the current of my inductor as the applied potential across the inductor divided by the impedance of the inductor. And here's where it's nice to have some of this phasor stuff. Okay. I could have just done this as, you know, something like cosine of omega t divided by j omega L. And then we don't like to have the, excuse me, I shouldn't do that. I should have done this, e to the j. So we could do this two ways. One is that we do our e to the j omega t divided by j omega L. We move our j to the numerator. So we get negative j e j omega t over omega L. Then we expand back out our Euler relation and throw out the imaginary term. So I end up with something that says negative j, put j sine of omega t over omega L. Notice I'm throwing out the cosine bit because that one's imaginary now. This one is real, and the negative j times the j just gives me a 1. So I end up with sine of omega t over omega L. That's if I, introduce the imaginary stuff, write everything in terms of Euler's relation and impedances, calculate everything out, and then throw out the imaginary piece at the end. The other way to do it is to just use our phasor notation, this sucker. And what do I have there? 1 omega t plus 0 degrees divided by omega L 90. And then we just apply our rules. We should get a magnitude of 1 over omega L. And then we have a division. So we should have omega t minus 90. And indeed, we should see that if we do omega t minus 90, that will give us the sine of omega t back. In fact, how do we see that? Well, let's go ahead. We have 1 over omega L. We don't touch that. And don't forget that this angle is with respect to the real axis. So we could put cosine of omega t minus 90 degrees. And then we use our angle summation formula. This would be, say, cosine of omega t, cosine of 90 degrees. And you definitely need to have these angle summations memorized. Sine of omega t, sine of 90. And cosine of 90 is, 0. This gives us 0. Sine of 90, that gives you 1. And so at the end of the day, you end up with omega L sine of omega t, which we expected anyway. So that takes care of the phasor notation. Okay. The other thing that I'll mention, and this is more just a terminology bit, is I keep mentioning the complex plane and phasors. Okay. Sometimes you might see this whole idea encompassed in a larger terminology. What this is called really is the frequency domain. Frequency domain. Okay. The reason for that, and I'll highlight this as well, generally, you will not see an angle written as omega t plus some angle. I used 0 here. Okay. Generally, you will not see that. Okay. The reason for it, if you apply a voltage supply of omega, okay, it is assumed that your circuit will have the same frequency in its response. I'll say that again. If you're applying some sort of voltage or current supply at a frequency of omega, it is assumed that your circuit will respond with the same frequency. In other words, the current through your inductor will have the same frequency. Or the current through your resistors will have the same frequency, and the capacitors will have the same frequency. So we, again, are lazy. We are not going to write this omega t in here. That is assumed. The only thing that's important is at what angle do you start with? The initial starting angle. The phase. Okay. And then it's assumed that that phase, this angle, will increase at the same rate, that omega t. Okay. It will increase at the same rate as time progresses. So generally, you will not see that omega t actually written. The important piece of information is the starting angle. It's assumed that everything in the circuit will progress at the same rate, at the same omega. Okay? Okay. So I think I'll leave it there. That's just a brief introduction to phasors and kind of the notation piece. Okay? Maybe the last thing I'll mention to you is that this should feel awfully familiar to a coordinate system that you've actually dealt with before, namely polar coordinate system. Right? If you go back and look, what we've really done is gone from a Cartesian system where you have a real component and an imaginary component, and we convert it into a magnitude and a direction. what we've really done is gone from a Cartesian coordinate system into a polar coordinate system. Okay? So just be aware of that. I just thought I'd throw that in there just as a final piece for you. Okay? So next time I'll just run some examples, and part of the reason why I wanted to use this notation is that several of my example problems use this phasor notation right off the bat. So I just wanted to give you a sense of that, and we'll probably solve it both in terms of the Cartesian system, and then I'll solve it again in the phasor system, just to give you an idea of the advantages of treating it according to that phasor notation. Okay? So, hey, I thank you for your attention. Keep up the good work. I'll see you next time.